I am Dr. Bindhu, Assistant Professor, Department of Science and Humanity, Emmanuel Research College of Engineering. My topic, Logical Connectives. Propositions. A proposition is a declarative sentence that is either true or false. Then someone declarative sentence, that sentence is true or false, it is called the proposition. Examples are propositions. The moon is made of green cheese. This statement is a declarative sentence. It is a proposition. Then another one, Toronto is the capital of New Jersey. Toronto is the capital of Canada. These statements are true. It is called a proposition. Then 1 plus 0 equal to 1. This statement is a true statement. It is a declarative sentence. And then other one example, 0 plus 0 equal to 2. This sentence is a false sentence. It is called the proposition. Propositional logic, constructing propositions, propositional variables P, Q or S. Then take the some one small letters, then propositional variables. The proposition that is always true is denoted by T and false is denoted by F. Then compound propositions, then constructed from logical connectives, and then other propositions are, then other symbols are used sometimes. The negation symbol is given there, conjunction, disjunction or inclusive, then exclusive or implication and biconditional. Truth table. Logical operators are defined by truth tables. The negation truth table is, then P variables false, true. Then false value is negation of P is true, and then P value is true, then negation value is false. Then next table is a conjunction, disjunction, exclusive or conditional and biconditional truth values. PQ truth values are given there, true true, true false, false true, false false. Then P and Q value is true, true true true, then true false false, false true false, false false false. Then P or Q truth values true true true, true false true, false true true, false false false. Then P exclusive or truth values true true false, true false true, false true true, false false false. Then same truth values are false, different truth values are true. Then conditional, then implication. True true is true, true false is false, false true is true, false false is true. Then biconditional truth values, true true is true, true false is false, then false true is false, then false false is true. Then same truth values are true and the different truth values are F. Then implication, this logical conditional, then implication, other name is a conditional. This statement is if then statement. Then if is a given statement, then is a proof conditions. Then implication is a if then statement. Then implication is different ways of expressing. Then if P then Q, one form is if P then Q, then another one is if P implies Q, then if P comma Q, then Q unless negation P, then other one is P only if Q, then Q when P, then Q whenever P, then P is sufficient for Q, then Q is necessary for P. Then a necessary condition for P is Q, then sufficient condition for Q is P. Then if P then Q, P is a antecedent value. Converse counterpart positive and inverse definitions. Then statement P implies Q statement is a given there. Then Q implies P is called the converse of P implies Q. It is called the converse definition. Then other definition is a contrapositive definition. Negation P to negation Q to negation P of is the contrapositive of P implies Q. Then next definition of inverse definition, negation P to negation Q is the inverse of P implies Q. Then biconditional form, then P if and only if Q. It is read as P if and only if Q. Then P is necessary and sufficient for Q. If P then Q, and converse part is if Q then P. Next way is P if and only if I double F. It means if and only if P if and only if Q. Precedence of logical operators. Then operators are negation, and, or, implies, and biconditional. Then precedence value of negation operator, precedence value is 1, and operator precedence value is 2, then or operator precedence value is 3, and biconditional operator precedence value is 4, then biconditional operator then precedence value is 5. Then P or Q implies negation R is equivalent to P or Q implies negation R. Then this statement is a same statement if the intended meaning is P or Q to negation R. Then parenthesis must be used. Then tautologies, contradiction, and contingencies. Then tautologies means this is a one propositions, all the values are, all the truth values are true. It is called the tautology. Some one proposition, then the whole proposition value, last final value is a true, then proposition is called the tautology. Then example P or negation P. The contradiction is a proposition which is for false. All the truth values are false. It is called the contradiction. Then example P and negation P. Then logically equivalent. Then take the two propositions A and P and Q propositions. If P biconditional is a tautology, then logical equivalent means B biconditional Q is a tautology. It is called the logically equivalent. Two compound propositions P and Q are equivalent, then if and only if the columns in a truth table given their truth values agree, then P, Q and the negation P or Q and P implies Q. Then negation P or Q, truth values true, false, true, true. Then P implies Q, true, false, true, true. Then truth values are same truth values. So these two propositions are logically equivalent. The next one is propositional functions. Then proposition functions become propositions when their variables are each replace value from the universe. Then one statement P of x is said to be the value of the propositional function P at x. For example, then P of x from x greater than 0 and the universe of x being the integers. Then P of minus 3 is a false statement, P of 0 is false, then P of 3 is true. Then often the universe is denoted by U. The whole set, the universe is denoted by U. This example, U is the integers. Then example of proportional functions. Then one equation x plus y equal to z, it is denoted by r of x comma y comma z in three variables. Then write the r of x comma y comma z, and then u is the universal. Then take the integer set, find the truth values r of 2 comma minus 1 comma 5. Then one example, then r of 2 comma minus 1 comma 5, these values are substitute the equation x plus y equal to z. X value is 2, y value is minus 1, and the z value is 5. Then x plus y, then 2 minus 1 is 2, then z value is 5. This is not equal to 1, not equal to 5. This example is a false example. Then other one of r comma 3, r of 3 comma 4 comma 7, x and y value 3 and 4, 3 plus 4 equal to 7, z value is 7, then 7 equal to 7, and this statement is a true statement. Then r of x comma 3 comma z, then x value is x, y value is 3, and the z value is z, then x plus 3 equal to z. This statement is a false statement. Quantifiers. The two most important quantifiers are universal quantifier and existential quantifier. Then universal quantifier symbol is for all, and then existential quantifier is there exist. Then for all x p of x, and there exists x p of x. Then for all x p of x, denote p of x is true for every x in the universe. Next one, there exists x p of x, it means p of x is true for some x in the universe. The quantifiers are said to be bind the variable x in these expressions. Then universal quantifier. The universal quantifier for all x p of x, it is read as for all x p of x. Then other one is for every x p of x. Then example of p of x denotes x greater than 0, and u is the integers, then universal is integers. Then for all x p of x is false. Then p of x denotes x greater than 0, and u is the positive integers. Then condition x greater than 0, then for all x p of x is a true statement. If p of x denotes x is even, then u is the integers, then for all x p of x is false. Existential quantifier. There exists x p of x, it is read as for some x p of x. Then other one is there is an x such that p of x are for at least one x p of x. Then examples, p of x denote the x greater than 0, and u is the inverse. Then there exists x p of x, there exists means for some element x, then for some x p of x is true. It is also true if u is the positive integers. If p of x denote x less than 0 and u is positive integers, then there exists p of x is false. Then condition is x less than 0, then negative integers, then u is the universal set is a positive integer, so there exists x p of x is false. If p of x denotes x is even and u is then integers, there exists x p of x is true. Then integer set is positive or negative or given there, then this even number. There exists x p of x is true. Properties of quantifiers. The truth value of there exists x p of x, and for all x p of x depend on both the propositional functions p of x and on the domain u. Then example, if u is the positive integers and p is the statement x less than 2, then there exists p of x is true, but for all x p of x is false. Then next example, if u is the negative integers and p of x is the statement x less than 2, then both there exists p of x and for all x p of x are true. Then next example, if u consists of 3, 4 and 5 and p of x is the statement x greater than 2, then both there exists p of x and for all x p of x are true, but if p of x is the statement x less than 2, then both there exists p of x and for all x p of x are false. Precedence of quantifiers. The quantifiers for all and their exist have higher precedence than all the logical operators. For example, for all x p of x and q of x means for all x p of x or q of x. The next one, for all x p of x or q of x means something is different. Then negating quantified expressions, consider for all x f of x. Every student in CS 1820 has taken a course in Java. Here f of x is x has taken a course in Java and the domain is student in CS 1820. Then negating the original statement gives it is not the case that every student in CS 1820 has taken Java. This implies that there is a student in CS 1820 who has not taken Java. Then symbolically, then write negation for all x j of x. J of x means Java and there exists negation j of x. This is equivalent statement. De Morgan's laws for quantifiers. Then De Morgan's law, negation, there exists p of x. This equivalent statement is universal statement for all x, negation p of x. This negation true for every p of x is false. Then false, there is an x for which p of x is true. And this next negation for all x p of x, then existential quantifier, there exists negation p of x. It is a equivalent statement for negation. Then there is an x for which p of x is false. Then p of x is true for every x. Nested quantifiers. Nested quantifiers are often necessary to express the meaning of sentences in English as well as important concept in computer science and mathematics. Then example is every real number has an inverse. Is for all x there exists y, then x plus y equal to 0, where the domains of x and y are the real numbers. It is called the nested quantifiers. Translating mathematical statements into predicate logic. Then example, translate the sum of two positive integers is always positive into a logical expression. Then first rewrite the statement to make the implied quantifiers domain explicit. Then first, for every two positive integers, then if condition, if these integers are both positive, then the sum of these integers is a positive. Then second condition, then introduce the variables x and y. Then sum of two positive integers, then take the two variables x and y and specify the domain For all positive integers x and y, then sum of positive integers is positive, then x plus y is positive. Then the result is for all x, for all y, then x greater than 0 and y greater than 0 implies x plus y greater than 0. It is a positive. Why the domain of both variables consist of all integers. Thank you.